March 15, 1943. Malvern, England. The laboratory technician at the telecommunications research establishment couldn't understand why the experimental magnetron kept producing these strange, thin sheets of crystalline material as a waste byproduct. Dr. Robert Watson Watt, the brilliant physicist who had revolutionized British air defense through radar development, examined the translucent films under his microscope with growing fascination. These molecular chains, barely thicker than soap bubbles yet surprisingly strong, seemed to form spontaneously during the high-frequency electromagnetic experiments that powered Britain's most classified radar systems. What neither man realized as they discarded these curious sheets into laboratory waste bins was that they were witnessing the accidental birth of materials science's most ubiquitous creation. The mathematics of molecular transformation were being written not in chemical equations but in electromagnetic frequencies that would accidentally unlock the secrets of polymer chemistry. A discovery that began with desperate attempts to detect German bombers would ultimately reshape how humanity packages, stores, and transports everything from groceries to spacecraft components. The transformation had already begun in ways no one yet comprehended. The story begins not with plastic but with survival. By 1940, German aircraft were crossing the English Channel nightly, devastating British cities through bombing campaigns that killed thousands and threatened to break civilian morale. The Royal Air Force possessed brave pilots and capable fighters, but they were fighting blind. German bombers approached under cover of darkness, invisible until engine noise announced their presence directly overhead. British defenders needed eyes that could see through night and weather, electronic vision that could detect metal aircraft at distances measured in miles rather than yards. Chainhome, Britain's first operational radar network, provided crude early warning capabilities through massive steel towers that dominated the coastline. These installations, each requiring 240-foot transmission masts and 350-foot reception aerials, could detect incoming aircraft formations at ranges approaching 100 miles. Yet the technology remained primitive, dependent on enormous fixed installations that consumed incredible amounts of electrical power while providing only basic range and bearing information. The breakthrough came through understanding electromagnetic radiation in ways that previous generations of scientists had never imagined possible. Radar functioned through transmitting radio waves that bounced off distant objects and returned to sensitive receivers. The time delay between transmission and reception revealed distance. The direction of strongest return signal indicated bearing. But early radar systems operated on relatively long wavelengths that limited resolution and required massive antenna arrays to achieve useful performance. Dr. Watson Watt and his team at the Telecommunications Research Establishment recognized that shorter wavelengths would provide dramatically improved resolution while requiring much smaller antenna systems. Aircraft could carry radar equipment instead of relying entirely on ground-based installations. Pilots could see enemy formations approaching long before visual contact. Anti-aircraft gunners could track targets through clouds and darkness with unprecedented accuracy. The challenge lay in generating sufficient power at these shorter wavelengths. Conventional radio transmitters achieved high power through large vacuum tubes operating at relatively low frequencies. Scaling these approaches to microwave frequencies proved impossible with existing technology. The power requirements exceeded anything conventional electronics could provide. The solution emerged from the Admiralty's signal establishment through work conducted by Harry Boot and John Randall, two physicists who had been experimenting with resonant cavity designs. Their cavity magnetron represented a revolutionary approach to generating microwave energy. Instead of relying on conventional vacuum tube principles, the magnetron used magnetic fields to control electron flow through carefully designed resonant cavities. The device appeared deceptively simple, a cylindrical cathode surrounded by an anode containing multiple resonant cavities. Powerful magnetic fields generated by permanent magnets controlled electron trajectories as they spiraled outward from cathode to anode. As electrons passed the cavity openings, they induced electromagnetic oscillations at frequencies determined by cavity dimensions. The result was unprecedented microwave power generation in a compact, efficient package. Early magnetron experiments achieved remarkable success by the standards of 1940. The prototype devices generated kilowatts of microwave power at frequencies around 3,000 megahertz. This represented a quantum leap beyond anything previously possible. Radar systems using magnetron transmitters could achieve detection ranges exceeding 150 miles while operating from aircraft or mobile ground installations. Yet success brought unexpected complications. The intense electromagnetic fields generated by magnetrons created secondary effects that researchers hadn't anticipated. Laboratory technicians noticed that various materials placed near operating magnetrons underwent strange transformations. Metal objects sometimes developed unusual surface properties. Organic compounds occasionally polymerized in unexpected ways. Most puzzling were the thin, flexible sheets that appeared sporadically around experimental equipment. These mysterious films possessed remarkable properties that defied easy explanation. They were transparent yet strong, flexible yet resistant to tearing, lightweight yet capable of containing liquids without leaking. Chemical analysis revealed long-chain molecular structures unlike anything in contemporary materials science. The sheets appeared to be composed of simple hydrocarbon compounds that had somehow arranged themselves into unprecedented configurations. Dr. Jeffrey G., a polymer chemist working with the radar development team, began systematic investigation of these anomalous materials. His laboratory notebooks, preserved in the Imperial War Museum archives, document growing excitement as he recognized the significance of what magnetron experiments had accidentally produced. The electromagnetic energy was catalyzing polymerization reactions that conventional chemistry considered impossible under normal laboratory conditions. The key insight came from understanding how microwave energy interacted with molecular structures. The electromagnetic radiation generated by magnetrons operated at frequencies that corresponded to molecular vibration modes in certain organic compounds. When ethylene gas, a common laboratory contaminant, encountered intense microwave fields, the energy input triggered polymerization reactions that created long molecular chains. These chains, when formed under specific electromagnetic conditions, possessed properties that exceeded anything achievable through conventional chemical synthesis. By spring 1943, G's team had identified the basic process. Microwave energy at specific frequencies could induce controlled polymerization in various hydrocarbon compounds. The resulting materials exhibited strength-to-weight ratios that surpassed many metals while remaining completely transparent. More remarkably, these polymer films could be produced continuously through electromagnetic processing rather than requiring complex chemical synthesis. The military applications appeared obvious. Lightweight, transparent, waterproof materials could revolutionize equipment packaging for military operations. Radio equipment could be protected from moisture while remaining accessible for maintenance. Food supplies could be preserved for extended periods without requiring heavy containers. Aircraft components could be covered with protective films that added negligible weight while preventing corrosion. Yet the wartime focus on radar development meant that polymer research remained secondary to electromagnetic warfare priorities. The telecommunications research establishment dedicated most resources to improving magnetron power output and developing more sophisticated radar systems. The accidental discovery of electromagnetic polymerization received limited attention beyond documenting the phenomenon and ensuring it didn't interfere with primary research objectives. The production challenges seemed insurmountable with existing technology. Creating useful quantities of polymer films required precise control of electromagnetic field strength, frequency, and exposure duration. The magnetrons designed for radar applications generated far more power than optimal for polymer synthesis. Scaling down to appropriate energy levels while maintaining frequency stability demanded entirely new approaches to microwave generation. Meanwhile, conventional plastics industry remained focused on phenolic resins, cellulose derivatives, and other materials that required chemical processing rather than electromagnetic synthesis. The concept of using radio waves to create polymer materials struck most industrial chemists as impractical fantasy. Even researchers who accepted the laboratory demonstrations questioned whether electromagnetic polymerization could ever achieve commercial viability. This skepticism proved premature. As magnetron production expanded to meet growing radar demands, manufacturing techniques developed that would eventually enable controlled electromagnetic processing. The precision manufacturing required for radar cavity magnetrons provided exactly the technological foundation needed for polymer synthesis applications. The same factories producing magnetrons for RAF Fighter Command were inadvertently developing capabilities that would transform materials science within a decade. The electromagnetic frequencies that gave British pilots unprecedented night vision were simultaneously unlocking molecular transformations that would reshape civilization itself. The breakthrough came through understanding something that academic chemistry had completely overlooked. The electromagnetic fields generated by magnetrons didn't simply heat materials uniformly like conventional ovens. Instead, they created precise energy patterns that could selectively activate specific molecular bonds while leaving others untouched. Dr. G's team discovered that ethylene molecules, when exposed to 2,450 megahertz radiation at carefully controlled power levels, underwent polymerization at rates thousands of times faster than conventional chemical catalysis could achieve. The process defied everything polymer scientists thought they understood about reaction kinetics. Traditional polyethylene production required high temperatures, extreme pressures, and complex chemical catalysts to force ethylene molecules into long chains. The electromagnetic approach achieved the same results using nothing more than precisely tuned radio waves. The polymer chains formed spontaneously as microwave energy provided exactly the activation energy needed to overcome molecular bonding barriers. By autumn 1943, laboratory experiments had produced polymer films with unprecedented properties. These sheets, barely 1/10,000th of an inch thick, could support weights exceeding their own mass by factors of several thousand. Unlike conventional materials that became brittle when manufactured in such thin sections, the electromagnetic polymers retained flexibility while gaining strength through molecular orientation effects that occurred during the polymerization process. The electromagnetic synthesis created molecular structures that conventional chemistry couldn't duplicate. The microwave energy induced uniform chain growth throughout the material, rather than relying on chemical initiators that created weak points. The resulting polymers exhibited molecular weights far exceeding anything achievable through traditional synthesis. Individual polymer chains contained millions of ethylene units arranged in nearly perfect crystalline structures. Wing Commander Derek Jackson, liaison officer between the Telecommunications Research Establishment and RAF operational units, witnessed a demonstration that convinced him of the material's military potential. Dr. G's team had fabricated a polymer envelope capable of containing over 5 gallons of water while weighing less than 2 ounces. The demonstration involved filling the container with colored water, then dropping it from a height of 20 feet onto concrete. The polymer film stretched dramatically upon impact, but didn't rupture, bouncing back to its original shape with contents intact. Jackson immediately recognized applications for airborne operations. Paratrooper equipment could be packaged in these lightweight, waterproof containers that would protect sensitive electronics during combat drops. Aircraft fuel tanks could be lined with polymer films that would self-seal if punctured by enemy fire. Radio equipment could be encased in transparent protective covers that eliminated weight penalties while providing complete environmental protection. The production challenges remained formidable. Creating polymer films required maintaining electromagnetic field uniformity across large areas while precisely controlling power density. The magnetrons designed for radar operated at power levels measured in kilowatts. Polymer synthesis required power levels measured in watts, delivered with stability that radar applications never demanded. Developing equipment capable of controlled electromagnetic polymerization meant essentially creating an entirely new category of industrial machinery. Professor Charles Frank at Bristol University, consulting on materials research for the Ministry of Supply, proposed a solution that borrowed directly from radar manufacturing techniques. The cavity resonators used in magnetron production could be scaled and modified to create uniform electromagnetic fields suitable for polymer processing. Instead of generating maximum power output, these modified cavities would provide precise field control across processing chambers large enough for industrial production. The first prototype electromagnetic polymerization system, constructed in December 1943, occupied an entire laboratory room at the Telecommunications Research Establishment. The device resembled a massive radio transmitter more than conventional chemical processing equipment. Precise waveguides directed microwave energy into a sealed chamber, where ethylene gas underwent controlled polymerization under carefully monitored conditions. Early production runs yielded polymer sheets measuring several feet square, with thickness variations controlled to within microscopic tolerances. The electromagnetic process produced materials with consistency that exceeded anything achievable through chemical synthesis. Every molecule experienced identical energy input, resulting in uniform molecular weight distribution and crystalline structure throughout the finished product. The quality impressed even skeptical observers from traditional chemical companies. Imperial Chemical Industries, Britain's largest polymer manufacturer, sent technical representatives to evaluate the electromagnetic synthesis process. Their confidential report, declassified in the 1980s, acknowledged that electromagnetic polymerization produced superior materials while potentially offering significant cost advantages over conventional chemical processing. Yet commercial development remained constrained by wartime priorities and technological limitations. The electromagnetic equipment required vacuum tubes, precision metalwork, and electronic components that were desperately needed for radar production. Every magnetron dedicated to polymer research meant one fewer radar set for RAF Fighter Command or Royal Navy vessels. The Ministry of Supply allocated minimal resources to polymer development, while German submarines threatened Britain's survival. The scientific implications gradually became apparent to researchers working on both radar and polymer projects. Electromagnetic energy at microwave frequencies could induce molecular transformations that opened entirely new approaches to material synthesis. The same electromagnetic spectrum that enabled pilots to see through darkness could also create materials with properties that conventional chemistry couldn't achieve. Dr. Watson Watt himself visited the polymer laboratory in January 1944, observing demonstrations of electromagnetic synthesis with the same intensity he had brought to radar development. His technical notebook recorded observations that revealed his recognition of the discovery's significance. The electromagnetic control of molecular processes represented a fundamental breakthrough comparable to the discovery of radio itself. The ability to use electromagnetic energy for precise chemical synthesis could revolutionize manufacturing across countless industries. The timing proved crucial for post-war development. As radar production reached peak efficiency in 1944, manufacturing techniques had been perfected that would enable large-scale electromagnetic polymerization once military demands decreased. The precision tooling, electronic control systems, and production experience developed for magnetron manufacturing provided exactly the technological foundation needed for commercial polymer synthesis. Meanwhile, military field tests had demonstrated practical applications that civilian markets would eventually demand. Polymer films proved invaluable for protecting equipment in tropical environments where conventional packaging failed completely. The materials maintained integrity under temperature extremes, humidity levels, and chemical exposures that destroyed conventional wrapping materials. Soldiers discovered that these transparent, lightweight covers could protect everything from ammunition to medical supplies while adding negligible weight to their equipment loads. The electromagnetic synthesis process offered advantages beyond material properties. Unlike chemical polymerization that required high temperatures and toxic catalysts, microwave processing operated at room temperature using only electromagnetic energy and readily available hydrocarbon feedstocks. The environmental benefits seemed significant, though environmental concerns remained decades in the future for 1940s industry. Production economics appeared favorable once equipment costs were amortized across large manufacturing runs. Electromagnetic polymerization eliminated expensive chemical catalysts while reducing energy requirements compared to high-temperature chemical processes. The continuous nature of microwave synthesis promised higher productivity than batch chemical processing. Raw material costs remained minimal since ethylene could be produced from petroleum or natural gas using established industrial processes. The scientific community began recognizing that electromagnetic synthesis represented a new frontier in materials science. The same electromagnetic spectrum that had revolutionized communications and detection could also transform manufacturing. Researchers speculated about using different frequencies to synthesize various polymers, potentially creating materials with precisely tailored properties for specific applications. As 1944 progressed toward Allied victory, planning began for post-war applications of wartime technologies. Radar would transform civilian aviation and shipping. Jet engines would revolutionize transportation. Electronic computers would automate calculation and communication. An electromagnetic polymerization would create materials that would reshape how civilization packaged, stored, and protected everything from food to industrial components. The accidental discovery, born from desperate attempts to detect German bombers, had evolved into a technological capability that would define the material culture of the post-war world. The commercial breakthrough arrived through an unexpected source in February 1945. Unilever Limited, the consumer products giant, had been struggling with packaging challenges for their expanding line of household chemicals and personal care products. Traditional glass containers proved too heavy and expensive for mass distribution, while paper packaging failed to provide adequate moisture protection. Metal containers required strategic materials that remained scarce despite approaching Allied victory. Dr. Margaret Thornton, Unilever's chief packaging engineer, attended a technical briefing at the Ministry of Supply, where electromagnetic polymerization received brief mention, alongside other wartime innovations being considered for civilian adaptation. The demonstration of polymer film strength immediately captured her attention. Here was a material that could protect products while weighing virtually nothing, manufactured from petroleum feedstocks that would become abundant once wartime rationing ended. Thornton's subsequent negotiations with the Telecommunications Research Establishment revealed both the potential and the obstacles facing commercial electromagnetic polymerization. The prototype equipment could produce polymer films measuring several square feet, but industrial packaging demanded continuous production of materials measured in miles. The electromagnetic fields required for synthesis needed precise uniformity across processing chambers large enough for commercial operations. The engineering challenges multiplied when scaling from laboratory demonstrations to industrial production. Dr. G's team had achieved excellent results, processing small quantities of ethylene gas in carefully controlled laboratory conditions. Commercial operations would require handling tons of feedstock daily, while maintaining the precise electromagnetic field control that laboratory synthesis demanded. Professor Frank's modified cavity resonator approach offered a solution, but implementation required manufacturing precision that exceeded most industrial capabilities. The resonant chambers needed internal dimensions accurate to fractions of wavelengths at 2,450 MHz. Surface finishes had to minimize electromagnetic losses while withstanding industrial operating conditions. Temperature control systems had to maintain cavity dimensions, despite thermal expansion effects from high-power electromagnetic fields. Marconi Wireless Telegraph Company, which had manufactured magnetrons for radar applications, possessed the specialized metalworking capabilities needed for commercial electromagnetic polymerization equipment. Their Chelmsford factory had perfected techniques for machining resonant cavities to tolerances measured in thousandths of inches. The transition from radar magnetrons to polymer processing equipment required modifications rather than completely new manufacturing approaches. The first commercial electromagnetic polymerization system entered operation in August 1945, just days after Japan's surrender ended World War II. The installation at Unilever's Port Sunlight facility resembled a scaled-up radar transmitter, more than conventional chemical processing equipment. Massive waveguides directed microwave energy into processing chambers, where ethylene gas underwent continuous polymerization under carefully monitored conditions. Today, when you grab a plastic bag at the grocery store, you're holding the direct descendant of those mysterious films that puzzled radar technicians in 1943. The electromagnetic waves that saved Britain from German bombers had accidentally unlocked the molecular secrets that would revolutionize packaging forever. From desperate wartime necessity came the ubiquitous material that now wraps our sandwiches, protects our electronics, and lines our garbage cans. The next time you hear a microwave oven humming, remember that those same frequencies once powered the radars that defended London and simultaneously created the plastic world we live in today.